Carnot Cycle. What is the most efficient heat engine possible? First, let's define what we mean by a heat engine. A heat engine is any device that operates in a cycle and does work on the surroundings as long as heat is added to it. If we have a heat engine, it must do a net amount of work on the surroundings as long as we provide heat to it. We specify that the engine works in a cycle to ensure that it operates continuously. As long as we supply heat to it, it should do work. Energy storage devices such as batteries or flywheels are not considered engines because eventually they will run down and stop doing work. In a heat engine, we want to maximize the work that we get out of it while minimizing the amount of heat that we supply to it. To measure this, we define the thermal efficiency, which is denoted by the Greek letter eta with the subscript Th for thermal. And this efficiency is defined as the net work output divided by the heat input. We can also define the efficiency on a rate basis, and it would be equal to the rate of doing work divided by the rate at which heat is applied to it. Now, when we define the thermal efficiency, we have disregarded the sign convention for work and heat. We only consider the magnitudes of the heat and the work. Before we discuss what is the most efficient heat engine possible, let us eliminate those kind of engines which are impossible to make because they violate one of the laws of thermodynamics. These are known as perpetual motion machines. A perpetual motion machine of the first kind is one that has work output but no heat input. This violates the first law, and it would have a theoretical efficiency of infinity. A perpetual motion machine of the second kind is a little more subtle. This is an engine that does work while heat is supplied to it. The first law is satisfied if the work output is equal to the heat input. The efficiency of such an engine is 100%. However, this violates the second law. All the entropy that is added with heat must be removed over a cycle. There's entropy which is added along with the heat, but there's no entropy removed with work. The definition of a cycle is that all the properties must be restored to their original values over the cycle. There must therefore be heat loss from the engine to remove entropy. A heat engine, therefore, is a device that does work while heat is being supplied to it, but it must also reject heat. This is summarized in what is known as the Kelvin-Planck statement, which says that it is impossible for any device operating in a cycle to receive heat from a high temperature source and produce a net amount of work without rejecting heat to a low temperature sink. A real heat engine, therefore, is a device that does a net amount of work on the surroundings. It receives heat, QH, from a high temperature heat source, which is at temperature TH. It rejects heat, QC, to a low temperature heat sink, which is at temperature TC. Now, entropy is added to the engine along with QH. All the entropy added, therefore, must be removed along with QC. Now, QC is wasted energy, but it is necessary to carry away the entropy. We must therefore minimize QC. We can now list some engine design guidelines. We would like to minimize the entropy added along with the heat QH. We want to maximize the entropy removed with the heat QC. And we do not want to generate any entropy within the engine. This means that heat addition and removal must be reversible, and all processes within the engine must be internally reversible. We can now do an entropy balance over the cycle. Over a cycle, the change in entropy of the engine must equal 0. So delta S for the cycle, which is the integral delta Q divided by T, must equal 0. We can divide the heat transfer into two parts. First, the heat addition, and second, the heat rejection. Delta S for the cycle would equal the change in entropy during the heat addition minus the change in entropy during the heat rejection, and this must equal 0. Let us first look at the heat addition. The change in entropy during heat addition, delta S, is equal to the integral of delta Q divided by T. We want to minimize the entropy which is added. We can do this by adding heat at the highest temperature possible. This would be TH, the temperature of the heat source. We can show this process on a TS diagram. All the heat is added at temperature TH. This is isothermal heat addition. Now, we will talk very soon about how we would actually do this in practice, but let us assume that we can add heat isothermally. Since the temperature is constant, we can take T out of the integral, and delta S would be equal to 1 upon TH integral of delta Q. This would simply be equal to QH divided by TH. We can look at heat rejection in a very similar way. Delta S for heat rejection would be the integral delta Q upon T. We want to maximize the entropy lost, which means we should reject heat at the lowest temperature possible, which is the temperature of the heat sink, Tc. So we do isothermal heat rejection at the temperature Tc. If the temperature is constant, we'll take it out of the integral. So delta S for heat rejection would be 1 upon Tc, integral of delta Q. And this would simply be equal to Qc divided by Tc. Now to go from TH to Tc without increasing the entropy, we would have to do an isentropic expansion. So let us do an isentropic expansion to go from TH to Tc. Similarly, to go from Tc to TH without increasing the entropy, we would have to do an isentropic compression. This would be a vertical line on our TS diagram. This completes the cycle. This cycle is known as the Carnot cycle, and it consists of 4 processes. To go from state 1, which is at the temperature Tc, to state 2, which is at the temperature Th, we need to have an isentropic compression. To go from state 2 to 3, it's an isothermal heat addition. From state 3 to 4, which returns us to the low temperature Tc, is an isentropic expansion. And to go from state 4 to 1 is an isothermal heat rejection. All these processes are reversible. And an engine built using the Carnot cycle is therefore a reversible engine. We can do both an energy and an entropy balance for a Carnot cycle. The energy balance says that delta E, the change in energy over the cycle, equals QH, the heat added, minus QC, which is the heat rejected, minus W net, which is the work output. And this must equal 0. The entropy balance says that delta S over the cycle, which is equal to delta S for the heat addition minus delta S during the heat rejection, must also equal to 0. We have shown that delta S for the heat addition is QH upon TH, and we subtract from this delta S for heat rejection, which is QC divided by TC, and this must equal 0. If we take the energy balance, that QH minus QC minus W net is equal to 0, we can rearrange that to get the work output, which is QH minus QC. Similarly, if we take the entropy balance, which is QH upon TH minus QC upon TC equal to 0, we can rearrange it to write the ratio of the temperatures Tc upon Th, and this will be equal to the ratio of the heat transfer Qc divided by QH. We can now calculate the thermal efficiency for a Carnot cycle. The thermal efficiency is the net work divided by the heat input. The efficiency of a Carnot cycle, therefore, is W net divided by Q in. W net, we have just shown, equals QH minus QC. Q in this case, is equal to QH. So we can write the efficiency as being QH minus QC upon QH. This is equal to 1 minus QC upon QH. QC upon QH, we have also just shown, equals TC upon TH. The efficiency of a Carnot cycle, therefore, equals 1 minus Tc upon Th. The efficiency of a Carnot engine depends only on Th and Tc. As Th increases, the efficiency increases. As Tc decreases, the efficiency also increases. How do we build a Carnot engine that operates between the temperatures Th and Tc? First, how do we do isothermal heat addition and heat rejection? If we have a two-phase mixture, we can add heat to it while its temperature remains constant, which is at the saturation temperature. So the first thing to do is to find a working fluid whose critical temperature is greater than Th. The vapor dome will lie with its peak above Th. We can now take this working fluid and evaporate it in an evaporator. The temperature in the evaporator should be at Th minus delta T, where delta T goes to 0. This way we will get reversible heat transfer. We can select the temperature inside the evaporator by picking the pressure of the evaporator suitably so it lies just below Th. We can now have saturated liquid entering the evaporator and saturated vapor leaving it. To expand the saturated vapor, we can use an isentropic turbine. This is an adiabatic reversible turbine, and we will get isentropic expansion through it. Coming out of the turbine, we'll get a two-phase mixture. Now to reject heat from it, we can take that mixture through a condenser, which is at a temperature Tc plus delta T, which is the infinitesimal amount greater than that of the heatsink, which is at Tc. And we will reject heat Qc from this condenser. Again, we can pick the temperature of the condenser by picking the suitable pressure. We will reject heat from the condenser, and then we have to go back to the high temperature Th. We can do this by compressing the two-phase mixture using a pump. We can drive the pump using the turbine, so we will still get a net amount of work out of the system. The pump, again, is assumed to be isentropic. This completes the cycle. If we now put a box around this device, this is a Carnot engine. We are supplying heat QH to it. We are rejecting heat QC from it. And we are doing a net amount of work, W net. We can, in principle, build a single-phase Carnot engine using a gas which is contained in a cylinder. We compress the gas with a piston. The first stage of the Carnot cycle is isentropic compression. We insulate the cylinder to make it adiabatic, and then we compress the gas reversibly until its temperature reaches TH minus delta T. The second stage is isothermal heat addition. We bring the cylinder in contact with the thermal reservoir, which is at the high temperature TH. The gas now expands as we transfer heat QH to it. We then go to the third stage, which is isentropic expansion. We let the gas expand further until its temperature reaches Tc plus delta T. Finally, we have isothermal heat rejection. We bring the cylinder in contact with the heat sink at Tc, and we remove heat Qc from it. We can show a Carnot cycle on both TS and PV diagrams. The first process is isentropic compression, which appears as a vertical line on the TS diagram, and it will appear as the curve PV to the power gamma is equal to constant on a PV diagram. The second stage is the isothermal heat addition, and this would appear on the PV diagram as the curve PV is equal to a constant. 3 to 4 is the isentropic expansion, and finally 4 to 1 is the isothermal heat rejection. To summarize, the Carnot cycle is a cycle for a reversible engine. The efficiency of a Carnot cycle equals 1 minus Tc upon Th. The efficiency depends only on the temperatures Th and Tc. If Th increases or Tc decreases, the efficiency of the Carnot cycle increases. A Carnot engine can be made using either a single-phase or a two-phase working fluid.